So our second talk of the session is a UW postdoctoral alum, Ben Erichson, who's now down at Berkeley, working with Michael. And he's going to be talking about these new work on physics-informed autoencoders. And so, all set. Okay, good.
Okay, can you all hear me? I hope. Okay, first, thank you for having me here today. Great pleasure to be back. So I will talk about physics-informed autoencoders. It's joint work with Michael and Michael. Pretty recent stuff. So let me start at the beginning. So what is machine learning about, right? Traditional, I have a set of inputs and I try to map it to a set of targets. And if you give me a set of training data, what I'm normally doing, I formulate an empirical risk minimization problem to find a candidate model which best fits my data. And if I have a very expressive model, I might add some regularization in it. But often this kind of regularizer we use might be not physically meaningful. So my interpretation of physics-constrained learning is that we want to inform the model by exploiting some prior knowledge about the data we have. And one way is to do this to formulate a physically meaningful regularizer. And this is particularly true for problems like we have in fluid dynamics, simple fluid flows, or also in climate data, more general in the realm of dynamical systems. So you can ask the question, why do we want to do this? I mean, we have heard this morning already, maybe if I have a good model, my model implicitly learns something about the physics. I think that might be true if I have a large set of data, but quite often I have to train with a limited set of data. And maybe the data I have do not contain enough information about the physics, so I can help to train the model by explicitly modeling some of my knowledge into it. And this becomes, I think, more important in scientific problems where we want to extrapolate, right? So in computer vision problems, traditionally, I just want to interpolate my data, right? And it probably does not matter what kind of regularizer I use as long as it works. And I also do not try to integrate the model at the end. At the end, I want to say, okay, I give a puppy dog in, say it's a puppy dog. But in scientific problems, kind of often I want to extrapolate a couple of time steps ahead. I have no knowledge about like climate prediction and so on. And I think here that's the hope where physics-informed learning more generally might help me. I'm not saying that I solved the problem here today, but it's maybe a step towards this direction. I think we hear some other talks about this as well, and you might hear a different definition about physics-constrained learning, but okay. Let me start at the beginning with the problem set up for what we do. So, you might have guessed it from the title. So here, the regularizer we try to design is one that preserves stability in the model. So, what assumes that that we have a dynamical system which can be modeled as shown here in equation 2, where this curly alpha evolves a state in time. Very basic setting, so X is my state. I should say, and either is an error term which captures all model errors. Okay, so in practice, I don't have access to the actual state, but I have some measurements, which I might be given by a sensor, and those measurements can be high dimensional. So I have a function g of x, which generates and gives me my measurement y. And then this curly guy here again, it's an error term which can capture some measurements for errors. Okay, so what do we want to do now? So we want to map an observation at y at time t to y at t plus 1, so one time step into the future. And to do this, we use an autoencoder type of model. And this idea is not new. There's some neat work done already in this realm. So what our idea is here that we might want to regularize the dynamics at the end. But let me first tell you a little bit more about the decoder. So the decoder tries to approximate this function g here, and the encoder tries to approximate the inverse of g. And if the encoder gives me a good approximation for the inverse of g, then my dynamics omega should be an approximation for this curly alpha here. So there is actually no reason, if I train it in this way, that omega is capturing some of the dynamics here, right? I mean, the whole thing is trained in a joint framework, so the dynamics can be also learned by the encoder and decoder. So we have to regularize or preserve that the encoder, becomes an inverse of the decoder, so basically the encoder is the inverse of G. The encoder is, approximate G inverse. And if that is true, then the hope is the only thing what can map y t to t plus 1 happens here in this dynamics block, whatever that is. Throughout this talk, I assume this is a linear layer, but this could be also a non-linear layer or an ODE or whatever you want to cook in there. Okay. So let me formulate first the physics agnostic model. So what I would do if you give me some training data, well, I minimize the mean squared error to train my phi, omega, and psi. And then I have here this additional term which maps yt to yt, so that preserves that the encoder becomes an inverse of the decoder roughly. So that's during training time, and now during inference time, I might not want only to go one time step into the future, but several time steps. So how can I do this? I basically form a function iteration and compose my model several times together. So the input of the first model is the output of my first step is the input for my second step, and so on. So I get this guy here in phi. And now again, so if phi is roughly the inverse of psi, then basically those terms will cancel, and I get this guy here in equation 6. And now, well, it is interesting to think about omega, right? Yeah.
In phi, what's wrong with just applying omega a bunch of times? Why do you need to keep encoding and decoding in the middle?
Right, so because, good question. I mean, the idea is that they cancel out anyway if I train it right? And in fact, so I could start like in the reduced order model setting, right? I just compress my data. What you see is maybe you end up to map your data to a space which is good for reconstructing the data, but not good for mapping it to a future state. And I will come back later at a slide to show the difference. Because this would happen, right? I could just crank up omega here, lambda here a lot. So basically it mainly learns the map from y to yt, from t to t plus 1. From t to t, the inverse. And not so much focusing on the prediction step, but then you get a very different coordinate space. So it makes sense in order to get good prediction that you learn this in a joint setting.
Y from a lower dimensional space. Right?
Say again?
I mean, Y is in a lower dimensional space than X, right?
And Y is in a higher dimensional space. X is in a lower dimensional space. So the state, I assume that here, it does not need to be necessary that way, but we assume that our state is lower dimensional than our measurements. Or the underlying, put it in a different way. The underlying state might be low dimensional, right? Or has a.
So either way, a right inverted and a left inverted, right?
Yeah.
One's invertible and the other's not.
Yes, you can put it that way. Okay, so we want to think here about this omega. So, well, we know that kind of if we use 6, then if all the eigenvalues of omega within the unit circle, then this model is stable. If they're not, this model is not unstable. So now if we assume that our actual underlying model on this side here, curly R is stable, we want to train a model which is also stable. So that's the whole idea here. Okay. The problem is, well, it's difficult to deal with complex eigenvalue decomposition. To kind of compute the derivative of a complex eigenvalue and eigenvector is a bit nasty. So an ad hoc way would be, well, I use weight decay. Sorry. There's like anything. Well, okay. It comes in a second. I might have covered around my slides. Sorry for that. Well, okay. So we use here. I mean, probably everyone knows. Who knows about Lyapunov stability? Okay, so I don't have to talk so much, right? So an idea from about 120 years ago. Formulated, I think it was known even before then, but rigorously formulated by Alexander Lyapunov, a Russian mathematician and student of Chebyshev. And probably I don't have to explain the details here since you're all familiar with this. But roughly the idea is that a dynamical system is stable if all trajectories starting in an arbitrary close all of radius delta and remain forever in a radius or in the ball of radius epsilon. And now if the dynamics are linear, then we can check this property by the eigenvalue analysis or by computing the eigenvalues of in our case of omega. Okay, so here is my weight decay slide. So one way is I can use basically weight decay. If I crank up the amount of weight decay, it shrinks my eigenvalues towards the origin. So this is a bit a cooked up model, so I show later some more realistic examples. So here I kind of try to find an extreme model which is trained with a high temperature. Well, if you look to the eigenvalues and you would ask which of those models would you try to choose, I hope you would all say, okay, probably the right model will do better, just from looking to those plots here and using this idea of the diagnostic tool. And I show you some visual results, and where we go, this is the input, and I go 10 time steps. If I don't have, and I have the eigenvalues out, my dynamics diverge, and I get a really bad prediction. And the fine-tuned or regularized model with weight decay does a pretty good job here. But okay, so it might be not very elegant to fiddle around with weight decay here until I get this model, right? I mean, I always have to train it to the end and then tune weight decay. I can do auto-tuning during the process, but okay. So here another idea. Again, we use an idea from 120 years ago, Lyapunov's second method, and there's a great talk by Stephen Boyd, more generous about 120 years of Lyapunov method, which Lyapunov's method say a dynamical system is stable. If you can formulate this Lyapunov equation here, and where P is a symmetric positive definite matrix, and Q is an arbitrary symmetric positive definite matrix. So using this idea helps us then a lot, because the nice thing is now, well, we need to find just a symmetric matrix P. We can set Q simply to the identity matrix, because we just can plug in any symmetric positive definite matrix. So basically we have this guy here in 10, which we now need to solve. And we can use the direct method, so I don't want to dwell too much into the details, but basically we can use the Kronecker product to transform the Lyapunov equation into this new system of linear equations here, where vector kind of, it stacks all the columns of my matrix into a vector. And once I have this, well, I basically can use the pseudo-inverse to solve this problem. So this 11 might have not only or not a unique solution, but if I assume that this guy here is full rank, then basically you can ignore the second term, then it has a unique solution. And the nice thing, so really what we wanted to do here is now, well, I have P, and if I have P now, well, I can compute the derivative of the eigenvalue and eigenvector. So this is the whole task here, right? If you come here tomorrow or say I can compute the derivative of a complex eigenvector or eigenvalue, well, then you can skip the last couple of slides. But that's a trick we wanted to get. Well, we can handle P, we cannot handle the original omega.
Just make sure I understand, you're computing the derivative of an objective with respect to lambda and b, or you're computing the derivative of lambda and b with respect to something else?
We compute the derivative of lambda with question. So the derivative of an eigenvalue with respect to okay, screw me here.
Sorry, we gotta get probably figured out. So probably the objective, because you're gonna add this into your, you're gonna add this as a regular.
Yeah. So basically, well, the point that PyTorch is so nice and gives you actually I never implemented myself, but the point is you can auto-differentiate. Let me put it different way. You can auto-differentiate symmetric eigendecomposition. You cannot auto-differentiate a complex eigenvalue decomposition. So that's the point. So yeah, I should actually check. I have not checked what the underlying mechanics is. It's just, it's so easy with PyTorch. It gives you just a toolbox. But in general, yeah, that was the whole idea. How do we get a symmetric matrix we can handle? And again, the problem is, okay, so this only works if all eigenvalues are distinct. So you see, one of the crux here of this approach is, which we have at the moment, is that it is not exactly numerically stable. So it works in most of cases, but sometimes it breaks, and you might have to change some of the parameters. But we hope we can solve this, because I mean, using the direct method might be not the best idea. So what another idea is to transform it into a continuous time system, and then they can solve a Schur decomposition, which is the more stable way, but that is future work. Okay, anyway, now we have this this P, and what we do now is kind of adding to our optimization, our objective function, this additional penalty here, where we kind of penalize in some form the eigenvalues of P. And I will talk a bit more about this in a second, but so we use this penalty here, which might look very arbitrary from just looking to it, right? Because I mean, originally we started maybe to use a hinge loss at the beginning, that we say, okay, large negative eigenvalues of P get penalized more than small negative eigenvalues. But actually, if you dive a bit more into it, it turns out that's not a good idea. And the point is, so if you, well, we consider here a special case, the omega, we say omega is diagonalizable and Q is chosen in an appropriate way. Then 17 reduces to the system of linear equations here, and I can solve it for omega. And I plot here the relationship between the eigenvalue P and the eigenvalue of omega, how those two are related. And it's actually interesting to look to this plot. So that means if the eigenvalue of p is larger than 1, then the magnitude of the magnitude of omega is less than 1. Right? So on the other hand side, if the magnitude, or if p tends towards minus infinity, then the magnitude of omega tends towards 1 from the right side. So kind of having p very small is not so bad. The eigenvalues tends towards the unit circle. But what is really bad if p tends towards 0, then the eigenvalues diverge, or diverging dynamics here. So we have what's the idea of our regularizer is that we penalize small negative p's more than large negative p's, and there might be room for other penalties or improving this. So this was just the first choice, which worked in particular well in our experiments. But it might not be the end of the story. Okay. Let me show now how this works in practice. A couple of examples. So I will not talk so much. I'll introduce the flow path cylinder. I think canonical example, everyone knows it. With red paper from Steve or Nathan, I think pretty common. And the second example we consider are some climate data. We kind of considered here just a 64 by 64 grid zooming in into the region of the Gulf of Mexico, inspired also by one of Steve's papers. I thought that's a cool example. We use smaller examples here just because it's more convenient to train a network or to train a large number of networks. So I start with the prediction performance for the flow past the cylinder. And here I use no weight decay for training. And I show you 3 different models. So the green model is where I use a pretty large lambda. So basically it focuses on mapping YT to get a good reconstruction or learning a good inverse. What we would do traditionally. And it's interesting. So the eigenvalues I learned here, they're all, you don't see it in the plot. 3 of them are actually out of the unit circle, but they're pretty close to the unit circle. And that looks pretty much as if you would kind of compute the DMD modes also where I get the DMD and then look to the eigenvalues of the DMD, I would kind of get a very similar picture. But the interesting thing is, so this really does not do good for predicting future states. So the second one, the blue line, is now, well, I reduce this number here by quite a bit, and then I get a different picture here. So prediction becomes slightly better, and still two eigenvalues are out of the unit circle. And the red line is now adding this additional penalty. So it does not do much here, right? I mean, this looks not too bad, but it is pushing those 2 eigenvalues here within the unit circle. And now the prediction accuracy becomes substantially better if we go 100 time steps into the future. And let me show you the corresponding eigenvector. So we can compute the eigenvectors of the small omega and put it through the decoder. And again, this green line here, which does not do a good prediction job, but I mean the eigenvectors look pretty similar to the PUD modes and DMD modes, interestingly. The modes of the eigenvectors of the 2 other models, I don't know. I mean, I think they're much harder to interpret. I cannot see anything, but they do much better for predicting future. So I just show this to show it might be like a coordinate space which I use for reconstruction of my data might be not the best coordinate space I want to use for prediction. And that is why using a joint learning framework just probably better than kind of learning some modes or reduced order modeling, kind of decoupling those tasks first, embedding them in a low dimension space and then learning a model in this low dimension space. But I'm happy to discuss this and get your input later, just an observation here. So this is kind of some visual results again. So you would see this agnostic model here is pretty off by a couple of cases. I hope you see this. So here we go 100 time steps, not only 10 time steps, where our physics-aware model is getting it roughly right even after 100 time steps. Okay. Now I trained with weight decay, and those models become, so if you look to the axis, the physics agnostic model becomes actually pretty good as well, right? I mean, we are now on a log scale. So weight decay helps a lot, but now you can use our penalty to fine tune it. I did it just in a different tuning parameter here, right? You train the model and then you see, well, the eigenvalues are outside of the unit circle, so penalize it. And you get, in most cases, a better performance. I do not know. I mean, I have not spent too much time to fiddle around with this cover here. It could be if I fine-tune cover better that eventually I get more, flat align. But just to show you some examples. Here are the results for the sea surface temperature data. So I think that this is a more complicated problem, and you see kind of the eigenvalues are spread out or kind of pushed out of the unit circle quite a bit more distinct than on the examples before, compared to our physics-informed autoencoder on the right, and you see we get a better prediction accuracy here again. But it's a hard problem, so I mean, we cannot go really here that many time steps into the future, but the error gets quite a bit larger after, I think, 5 to 10 time steps. So here, a time step is 1 day. And we model also, the error here is for the fluctuations around the mean. I should just say this, right? I mean, just predicting the mean 5 to 10 time steps ahead is not that difficult, but modeling the fluctuation is a much harder task. And here's some visual results for 4 different examples. Our input, and this is at 5 time steps into the future. First example looks not so bad with the physics agnostic model, but if you look to example 3, here the sky is completely off, where our physics aware model is doing a bit better. So I'm not a climate scientist. I hope this is accurate enough to see something or not. But for me, it looks pretty good. Okay, so did I just propose here a new regularizer, which gives you an additional tuning parameter? I mean, we have heard about regularization quite a bit. There are many forms how you can regularize. Particularly with autoencoders, I have this bottleneck, which is important. How big or small do I make the bottleneck? I showed you at the very beginning a model with a very, where the bottleneck was not very small, and you get kind of those crazy models. And the last couple of models were a bit more fine-tuned or fine-designed so that you get actually good predictions. And the difference is, in some form what we do is just some form of regularization, but the hope is also that you can use it as a diagnostic tool and interpret what you're doing, right? I mean, I don't know, with dropout, how to interpret it. I mean, yeah, you can interpret it, but does it have a physical meaning? Maybe, maybe not. Bottleneck, sure, I can inform it maybe by the underlying or by the intrinsic rank of the of the problem. I know whether it's lowering or not. So based on that, I can design my bottleneck. Early stopping, again, depends how much time I have. Okay. So what we see is the physics-informed autoencoder can help to improve the generalization performance. The biggest problem I see at the moment with physics-informed learning is that we kind of design more complicated loss functions, right? You see most of the works is, well, we add something to the loss function and I give you a couple more parameters to tune with. So those terms might become more interpretable. That is good. And maybe the hope is that some of those terms I can automatically tune. I mean, for our case, well, I could write a for loop, increase our kappa until the model becomes stable. So that's not so difficult to do. So that's actually pretty neat. And what we're looking into next is well, extending. So far we just have considered a linear block omega, and next is that we want to look to building or looking into some nonlinear dynamics or looking to a recurrent network, and maybe to some parameterized layers. I think I forgot one thing to say, but actually I can use it here. So let me go back a couple of slides because this might be interesting. So what you see, there's a difference in the loss function, what I showed you. So here I have an additional term, yt plus 2. So I do not only train here 1 time step, but 2 time step. So I actually did this because I gave this talk last week and someone said, well, your omega might just... Perfect, okay. Just go to the last slide. If you want to have more information, paper is on our side.
Yes, Cam.
So you're trying to control the spectral radius of the omega matrix. Have you just tried a very simple norm penalty, like a Frobenius norm? Really, you want the 2 norms?
Yeah, so that's what I did with weight decay, right? So
Is that what weight decay?
Say again?
Is that what weight decay means?
Yeah, so that's what weight decay does, right? So you have Frobenius norm or regularized Frobenius norm of your matrix. And that works, right? I mean, it's nice. You can use it, but you have to fiddle around with the parameter. I think Sure. I just think it's more elegant. I'm not saying you should use it, but I mean the point is, well, you should think about, okay, there are different ways how you can probably incorporate or force the model that it preserves stability. And you can play around with weight decay, but what I showed you is, I mean, even if I tune weight decay, we get slightly better performance if you use our penalty. Yes. Oh well. I don't know where to start first. Yeah. Go. Whoever speaks.
I have a question about the eigenvalue to the cylinder flow. So there you know not, well, from physics, you know that the flow is not just, the eigenvalue shouldn't just be on the unit circle, but they should be very close on the unit circle. So could you take this approach to not just force them inside to the boundary?
Yes, so we have done this as well. What you have seen, our regularizer is kind of a clipped Laplacian, right? So where I set the positive values for p to 0, you can just leave this term in and it pushes the eigenvalues towards the unit circle. Problem is then that prediction accuracy goes down. I don't know why, right? So you get something which you expect to find from PCA, DMD, where you get nice eigenvalues, eigenmodes, but that might be better for interpretation, but it turns out not better for prediction. I do not know why, and I would love to understand this better. Just an observation we have here, so that is different. But yeah, in more general, right, I mean, you can come up with all kinds of prior whatever you want to do. Our objective was just to preserve stability, not to incorporate any other knowledge we have. Okay.
I'll actually hold questions until, so right when we go to lunch, we'll have plenty of time for that, and I encourage you to talk to Ben. Thanks, Ben. Yeah.